Hi, my name's Eduardo, and in this video, I'm going to explain how temperature affects chemical equilibrium using Gibbs free energy. The main idea behind this topic is the relationship between Gibbs free energy, delta G, and the equilibrium constant K. Gibbs free energy tells us whether a reaction is spontaneous. If delta G is negative, the reaction is spontaneous and favors products. If it is positive, the reaction favors reactants. We can also connect Gibbs free energy directly to the equilibrium using the equation delta G equals negative RT ln K. This equation shows that as delta G changes, the equilibrium constant K also changes. To understand the relationship, we can look at key variables. For instance, here we have the T, which is the temperature variable, which plays a role in determining how energy is distributed in a system and how equilibrium shifts. Then next we have enthalpy, delta H, which represents the heat absorbed or released during a reaction. This tells us whether the reaction is endothermic or exothermic. Then we have entropy, or delta S, which measures the disorder of the system. Reactions that increase disorder are generally more favorable. And then another important variable is the heat capacity, Cp, which describes how enthalpy and entropy change as temperature changes. This becomes important when we compare reactions at different temperatures. Then we also use the gas constant R, which connects energy and temperature in thermodynamic equations. All of these variables come together in the equation delta G equals delta H minus T delta S. This equation shows how temperature directly affects the Gibbs free energy of a reaction. To model how equilibrium changes with temperature, we can combine these equations and analyze real data using a graph. This graph, which was found on the Chemistry Libre text, it shows how to model equilibrium changes with temperature. We can combine these equations and analyze real data using this graph. It's called the Van 't Hoff plot. It shows the natural logarithm of the equilibrium constant ln K on the y-axis and the inverse of temperature, 1 over T on the x-axis. From thermodynamics, we can rearrange our equations to get a linear relationship where the slope of the line is negative delta H over R and the intercept is delta S over R. In this graph, we can see a straight line with a negative slope, which represents an endothermic reaction. This means that as temperature increases, the equilibrium constant K increases, favoring the formation of products. So by using this type of graph, we can model real experimental data and predict how equilibrium will shift as temperature changes. Overall, Gibbs free energy provides a powerful way to understand and predict chemical equilibrium, and tools like the Van 't Hoff plot allows us to connect theoretical equations to real-world data.